Alright, I'm going to very quickly run through the basics of ionic and covalent bonding. The first thing that you need to know is the definition for both. Ionic is a little bit longer, electrostatic, not electromagnetic, electrostatic force between oppositely charged ions. Covalent, a shared pair of electrons. Both definitions need to be learned. Both definitions get you 2 marks. You will not get a mark for saying ionic is the bond between a metal and a non-metal, or that covalent is 2 non-metals. You need to learn the definitions. However, that is a handy way of seeing which one is which. Ionic does occur between metals and non-metals, and covalent will occur between 2 non-metals. The other thing you need to do is to be able to discuss the properties, all right? So your typical property question is they might ask you, explain why something is strong, or explain why it's solid. Why does it have a high melting point? Why does it have a high boiling point? And all of these questions, all of them, can be answered in the same way, okay? I'm going to hone in on this part here. Solid, okay? What we all know how to do is draw those particle diagrams. And if you're drawing one for a solid, you would draw it like this. And what this diagram shows me is that all of the particles are touching, they are tightly packed. The reason that they're so close together is the forces between those particles are very strong. And if you've got strong forces holding the particles together, you'll require lots of energy to break those particles apart. Now, in order to get full marks, you just need to be able to be specific. What strong force are you trying to break? Well, if you've got a metal and a non-metal, and you know that it's ionic, you're going to say you're trying to break the strong electrostatic force between those oppositely charged ions, and that requires lots of energy to break. If you're given something where it's just non-metals, then you're going to say you're trying to break the strong covalent bond, and that requires lots of energy to break. So to get full marks, you need to be able to fill in electrostatic force if it's ionic, or simply just covalent bond if it's covalent. And then you always mention energy for a mark. That explains why something's solid, it explains why something's strong, it explains why it's got a high melting and boiling point. So the same type of answer, even though they can ask the question in a few different ways. The other thing they could ask you is explain why something is a liquid or a gas. Why does something have a low melting point? Why does something have a low boiling point? So again, I'm going to go back to a particle diagram. I'm going to draw one for a gas, all right? If we draw one for a gas, we can see that the particles are far apart. If the particles are far apart, we can say that there must be a weak force between them. And if there's only a weak force between the particles, then it doesn't require much energy to break. Okay, again, to get full marks on this, you need to be specific. But luckily, with liquid gas, with low melting point, low boiling point, the answer is always the same. There's only one type of weak force, and it is called intermolecular. So you don't even need to look at what you've got. All right, if they're asking you why is something a liquid, gas, low melting point, low boiling point, you're just going to say weak intermolecular forces, they don't require much energy to break. Okay, that is the only weak force. That will always be your answer. And intermolecular forces are always weak, never ever write that they are strong. The other property you're asked about is conducting electricity. You'll be asked, why does something conduct electricity? Okay, regardless of what you've got, to conduct electricity, there must be charged particles that are free to move. Okay, so that's always going to be the structure of your answer. Some sort of charged particle that are free to move. Now, unfortunately, if you just say charged particle and you don't tell me which one, you're not going to get full marks. But luckily, there are only 2 types of charged particles. You can have delocalized electrons, or you can have ions. And you need to look at what they've given you to decide which one. If they're asking you about graphite or graphene or any of those other allotropes of carbon, like a carbon nanotube, they all have delocalized electrons. So you'll say that delocalized electrons are free to move and carry the electricity. If they give you a metal, so something like iron by itself, or sodium by itself, or copper by itself, you're also going to write that those delocalized electrons are free to move and carry the current. If they give you something ionic, all right, and remember, there are ones with metal and non-metals in them. So instead of giving you sodium, if they give you sodium chloride, a metal and a non-metal, you're going to say the ions are free to move. Also, if they give you an acid, something like hydrochloric acid or sulfuric acid, any type of acid, even though it's not ionic, acids do give you ions when they're dissolved in water, and you're going to talk about the ions are free to move. So the answer again is the same, you just need to pick which type of charged particle. You'll never get the mark for charged particle alone. The other thing you need to be able to do is draw a few dot and cross diagrams. If you know how to draw them, you don't need to continue watching. I'm just going to very quickly draw a few of the most common ones. So if they ask you to draw Cl2, you will draw two chlorines overlapping. This area in the center is for the shared electrons. First thing you need to know is how many electrons you're drawing. Chlorine is in group 7. That means for each chlorine, you are drawing 7 electrons. Okay, which means I should have 14 in total by the time I'm finished. And you need to decide whether you're putting those electrons on the outside bit or in the inside bit being shared. All right, to know how many electrons they're going to share, you just need to know how many they want to gain. If each chlorine has 7 electrons in the outer shell and they want to have 8, then each chlorine wants to gain 1, which means they share 1. So chlorine wants to gain 1, so it shares 1. But it's got 7 in total. The other 6, it doesn't share. The other chlorine does the same thing. It's got 7. It wants 8. If it wants to gain 1, it shares 1. So it shares 1, but it's got 6 more. All right, so just check that it's right. You should have 14 electrons, 7 each. You should have all of your electrons in pairs. You should never have any electron sitting by itself. And at the end, each chlorine should have a full outer shell. 2, 4, 6, 8, 2, 4, 6, 8. The next one, O2. Again, I'm drawing 2 oxygens with overlapping shells. Oxygen is in group 6, so each oxygen has 6 electrons. It wants to have 8. That means it will gain 2, so share 2. So it's got 6, it's going to share 2, so 1, 2. That means the other 4 electrons go on the outside. So I've drawn 6 in total, 2 being shared because it wants 8, other 4 not being shared. The oxygen over here does exactly the same thing, and I end up with this. Have I drawn 6 electrons for each? Yes. Are they all in pairs? Yes. Do I have 2, 4, 6, 8, 2, 4, 6, 8 full outer shells for both? I know that's correct. Nitrogen is in group 5, so each nitrogen has 5 electrons. It wants to have 8. If it wants to have 8, it needs to gain 3, so it will share 3. 1, 2, 3 in the sharing space. It's got 5, it's sharing 3. That means there are only 2 electrons left over. This other nitrogen does exactly the same thing. 1, 2, 3. Other 2 not shared. I've drawn 5 electrons for each nitrogen. I've got 2, 4, 6, 8, 2, 4, 6, 8 for each nitrogen, and all electrons are in pairs. Something slightly different over here, I've got NH3, so make sure you read the formula properly. I want 1 nitrogen and 3 hydrogens. So the thing that you've got 1 of, put that in the middle, and then have the hydrogens going around it. Make sure the hydrogen shells don't overlap with each other. They should overlap with nitrogen, not with each other. Again, nitrogen's in group 5. It has got 5 electrons. Each hydrogen has just got 1 electron. I'm going to start with nitrogen, all right? It's got 5. I know it wants 8, which means it will share 3. But this time I've got 3 sharing spaces, not just 1. If it wants to share 3, and there are 3 sharing spaces, it's going to put 1 electron in each space. But there's 5 to draw in total. That means 2 electrons are not shared. They go on the outside. Hydrogen's only got 1 electron. Hydrogen, that electron, it's in the first shell. And if you remember, the first shell can only hold 2 electrons. So it's got 1. And it wants 2 for a full outer shell, which means it's going to share 1 electron. So hydrogen's only got 1 and it shares it. Hydrogen's got 1 and it shares it. It's got 1 and it shares it. That will always be the case for hydrogen. Hydrogen will always share its only electron. You will never have electrons on the outside for hydrogen. Never, ever, ever. All right, 1 electron and it goes in the shared space. All my electrons are in pairs. I've got 8 electrons around the nitrogen and I've got 2 around each hydrogen. Everything's got a full outer shell. Then you've got carbon. Carbon is in group 4. It's got 4 electrons in its outer shell. Oxygen has got 6. Again, I put the one that I've only got 1 of in the center, and I got the oxygens going on either side. I'll start with carbon. Carbon's got 4 electrons. It wants to have 8. That means it needs to gain 4 more. If it wants to gain 4, then it needs to share 4. Now you've got 2 sharing spaces. It's got 4 to share and 2 sharing spaces. So I'm going to put 2 in that sharing space and 2 in that sharing space. It doesn't have any electrons left, okay? It's got 4, it's sharing 4. You shouldn't have any electrons on the outside for carbon. So no electrons on the outside for carbon, none on the outside for hydrogen either. Oxygen has got 6 electrons. It wants to have 8. It needs to gain 2. That means it needs to share 2. That 2 shared, it's got 4 left over it to bring me to 6 dots in total. 2 shared, 4 left over to bring me to 6 dots in total. So check. Have I drawn 6 dots for each oxygen? Yes. 4 dots crosses for carbon? Yes. Around oxygen, 2, 4, 6, 8. 2, 4, 6, 8. Around carbon, 2, 4, 6, 8. All electrons are in pairs. Alright, so they are your dot and cross diagrams. They come up every single year, so it is definitely worth practicing them.